Okay, so apologies for last Thursday's lecture not having sound. Was messing around with some settings and didn't test carefully enough. I did test this morning. Should be recording sound unless there's some other weird bug. But this is one of the reasons why I strongly encourage you to take notes during lecture live. So we got a warm-up question here. Let's go through it. Hopefully you've had a chance to think about it a bit. So we're trying to prove two sets are equal. And from last time, in order to show two sets are equal, we're going to show double subset inclusion. So first, I'm going to pick any element from one of the sides. Let's say this side. Okay, and the relative good news about these problems is that there's sort of only one thing to do at most steps. So what does this mean by definition? By definition, we're taking X is in A and X is not in B union C. That's what it means to be in a relative complement. And now, not a lot to do with X is in A, but if X is not in something, maybe I'll put an and in here. If X is not in something, then X is in the complement. B union C complement. And last time we saw B union C complement was the same as B complement intersect C complement. This is from last time. So X is in A and X is in B complement intersect C complement. So X is an element of A intersected with B complement intersect C complement. And we just picked X arbitrarily, so our rule of universal generation gives, as X was arbitrary, A relative complement B union C is a subset of A intersection B complement intersection C complement. And now we got to do the other inclusion. X be an element of A intersect B intersect C, B complement intersect C complement. Unfortunately, these steps are pretty reversible. So X is an element of A and X is an element of B complement intersect C complement, which is equal to B union C all complement, again by De Morgan's laws for sets. So X is not an element of B union C, therefore X is an element of A relative complement B union C. And again, X was arbitrary, so we can conclude that A intersection B complement intersection C complement was a subset of relative complement A, B union C. And now we have both subset inclusions. As both sets are subsets of one another, we get to conclude A without B union C is equal to A intersection B complement intersection C complement. Okay. Questions about that warm-up? Hopefully that one's feeling good. Okay. So last time we carefully showed, yeah, so much writing. It's, it's a proof. It's not a calculation. So it takes enough writing to explain to your reader what's going on. It's a lot less writing than you would do in an English class if you're writing an essay. So depends on what you're comparing it to. More than you're used to in math, but still less than a lot of other classes. A lot less than many other sciences, if we're being honest. But okay. So last time we proved this fact that we just used, B union C complement is B complement intersect C complement. And as I mentioned, this relates to De Morgan's law. From logic, not B or C logically equivalent to not B and not C. All right, see the parallels here. And I mean, that's not a mistake. Not a coincidence, I guess I should say. When proving this statement, we were using this fundamental logic concept in order to prove this statement. And so lots of our logic laws have corresponding set laws that go with them. So if I look at A, that's going to be the same as the complement of A. So this is your law of double, instead of negation, now it's double complement. And we've seen one of De Morgan's laws, but you can do it the other way as well. The complement of the intersection is the union of the complements. And then I also want to mention associative laws. And same with intersection. And others as well. There are more in the theorems and documents, theorems and definitions document, but like the distributive laws carry over similarly as well. But the associative laws are important because it says in this last example we were a little bit more careful than we needed to be. If you have a bunch of intersections or a bunch of unions, the order in which you list them doesn't really matter. And because of that, we can actually do, just like we have big sigma notation, we can have big union notation. So if we write something like union I in I of A sub I, this is a union of a bunch of things all together. This is the set of x's such that there exists I in I, x is in A sub I. And similarly, we can have an intersection of sets, and this is the set x such that for all I in I, x is in A sub I. And here, capital I is called an index set. Can I repeat what I called the notation. Sure, I mean, this is just a big union and a big intersection. So this big union is the union of all the sets AI indexed by this set big I. It's the set of elements X such that there exists an element I in big I where X is in the set AI. Second one is big intersection AI. It's the collection of all X's such that for every I in our index set, A is an A sub I. So this index set might be finite. Right? I could have, like my example from before, I could have A intersection B complement intersection C complement, in which case my index set I would be A, B complement, and C complement. But we can also have infinite index sets. So I want to do an example now. A sub n is going to be the set of integers such that x is bigger than n, and there exists b also in the integers so that x is equal to n times b. And now my question is going to be, what is the complement of the union over all n at least 2 of A sub n? So let's talk through what this means. A particular set is all of the numbers that are a multiple of n. So, but not n itself. So A sub 2 is, I need x to be bigger than n, so it can't be 2. It can't be 3, because 3 is not a multiple of 2. So I'm getting 4, 6, 8, 10, and so on. And A sub 3 is going to be 6, 9, 12, 15, and so on. And A sub 4 is 8, 12, 16. A sub 5 is 10, 15, 20, 25. Okay, you get the idea. Yep, x is equal to n times b. So these are my sets. I'm unioning them all together, even though there's infinitely many. I'm using my big U notation to get them all together, and then I'm taking a complement. So my question is, what am I getting out of this set? What is this set describing? And let's make this actually z plus, so we can talk about the universe being positive integers. Well, let's try. Let's see what we get. If I'm starting with all of the positive integers, and so on, I'm taking the complement of a union, which means I'm saying I'm not in any of these sets. So from A2, I get rid of 4, 6, 8, 10, 12, 14, so on. And then from A3, I get rid of 6 and 9 and 12 and 15. From A4, I get rid of 8, already gone. 12, already gone. From A5, I get rid of 10, 15, 20, 25. What am I left with at the end? Yeah, really good. This is a description of the prime numbers and also 1. So this is capturing the primes. Excuse me. Okay. So 2 comments I want to make about this. The first one is that De Morgan's laws hold even when you have an infinite number of these sets. So this set is equal to the intersection of the complement. This is by De Morgan's laws. And that's something that's important to say because we could prove it for finite sets using induction, but once our index set is infinite, we don't actually have a way of proving that right now. But it also lets me transition into talking about our next topic, which is divisibility and prime numbers. So let me be a little bit more careful about what I mean. So if I pick 2 integers, we say B divides A, which we write with a bar like this. B divides A if there exists an integer n such that A is equal to B times n. And equivalently, we can say B divides A, or A is a multiple of B. Those two things mean the same thing. Why B divides A? If we divide both sides by B, we get A over B, and that's equal to some integer. Okay, so 5 divides 30 because 30 is equal to 5 times 6. Okay. And now an integer p that is bigger than 1 is called prime if it has exactly 2 positive divisors. So if B divides A, then B is a divisor of A. So if we have exactly 2 positive divisors, then you are prime. What do those 2 positive divisors have to be? Well, those 2 positive divisors are going to be 1 and P, because we'll see in a moment that 1 divides any number, and P always divides itself. So every positive number has at least 2 positive divisors, and it's called prime if that number is exactly 2. If you are not prime, by the way, that means you are composite. Okay. And so we want to do some work with prime numbers and divisibility. We want to prove some theorems about them. So let's get some practice doing that. So theorem. If a is greater than 0 and b divides a, then b has to live between negative a and positive a. Basically, this means you can't have a number that's bigger in absolute value dividing something that is smaller and get an integer out. So this seems like something that should be obvious, but we still need to prove it, right? We need to write down a careful argument that justifies it to someone who isn't sure, right? Why? There's so many numbers. Why can't a bigger number ever be a multiple of a smaller number? And all we have is our definition of what it means to divide. So let's try a couple of cases. So proof. Case 1, let's look at b as positive. Okay. So if a is positive and b is positive, a is greater than 0, b is greater than 0, and a is equal to b times n, then n also has to be greater than 0, right? Can't have a positive, and a negative. And since n has to be an integer, if you're bigger than 0 and you're an integer, n has to be greater than or equal to 1. But this means that a is equal to b times n, which is greater than or equal to b times 1. N is bigger than or equal to 1, so anywhere where I see an n, I can replace it with a 1 as long as I'm making my equation smaller, which is equal to b. Or a is greater than or equal to b. And since b is positive, this is greater than 0, which is greater than or equal to negative a. So I have that b is stuck between a and minus a in this case. Okay, but that only works if b is positive. If b was negative, then n would also be negative. So let's look at that separately in case 2, which is b is less than 0. Now, we could write something very similar. We could say if a is greater than 0, b is less than 0, so a is b times n, n must also be negative, right? You can repeat your same argument. How did I get this last line? So I know that a is greater than or equal to b. And I know that b is greater than 0. And since a is greater than 0, that must mean negative a is less than 0. And I'm just stringing all of those inequalities together. A greater than or equal to b, which is greater than 0, which is greater than minus a. Okay, so if b is less than 0, there's a nifty trick we can do that saves us a bunch of work. We can reuse case 1. If b is less than 0, then negative b is greater than 0. So by previous case, sorry, not ready to say this yet. also negative b divides a as well. If b divides a, the negative b divides a because a is equal to negative n times negative b. So now, by previous case, by case 1, I know that negative a is less than or equal to negative b is less than or equal to a. And if I multiply everything by negative 1, a is greater than or equal to b is greater than or equal to negative a. So I've reused case 1 in case 2 to save on a little bit of work. That makes a nicer looking proof. And then I just have to be careful. My last case is when b equals 0. But if b equals 0, it's very easy. A is greater than 0, which is b. So a is greater than or equal to b is greater than or equal to minus a. Again, because if a is bigger than 0, I know minus a is smaller than 0. So, simple looking statement, not the simplest proof. We had 3 separate cases with different arguments in each case. Which is why we like working with divisibility, because you can ask questions that are easy to understand, but you get some good practice writing down proofs. Okay, so let's have you prove some things. So prove a divides a divides minus a, 1 divides a, and a divides 0. So for each one of these, you should be able to use the definition of what it means for this to divide this to prove these 4 statements. So let's start with this first one. Why does a divide a? I want to write this down in the form a equals some multiple of a. Yeah, really good. A is equal to a times 1. How would I prove this second one? Yep, same with negative 1. A is equal to a times negative 1. 1 divides a because what's next? Yep, I'm just swapping things around. A is equal to 1 times a. This time the multiple is a. This is the 1. And how about, why does a divide 0? Confused about the third one. Okay, so remember, b divides a if we can write the equation a is equal to b times n, and we can put an integer here. So on this third one, 1 divides a means A goes here, right? The B divides A, so the A comes over to this side, is equal to B, here B is 1, times some number. And the number we're multiplying by is A again. Good question. Yeah, and the last one, 0, we have to write as A times something, and the something is 0. So A divides 0. Yes, sorry. Good catch. Negative A, yep, we bring what's on this side over here. Negative A is equal to A times minus 1. Yes, these are all, A is an integer in all of these cases. When we talk about divisibility, we require both A and B to be integers. We're not concerned. So is, good question, I like that. Let's look at this. Does 0 divide A? What would this mean? It would mean A is equal to 0 times some number. Is there any number I can put in here that will make this true? Yeah. No value makes this true. Unless it's a 0. So this, we can now raise the question, does 0 divide 0? And according to this, we're going to say yes, 0 is a multiple of 0. So 0 is a divisor of 0, even though it is true we do not let you divide by 0 in real life. But when we're talking about divisibility, 0 is a multiple of 0. That's not a controversial statement. 0 is a divisor of 0, a little bit messier. But for our discussion here, we're going to go with it. Okay, let's take our short break now. So take 2 minutes, go get some water, get up and stretch. We'll come back 9:08 and talk more. I'm also going to go get some water. Okay, I got 9:08. Let's reconvene focus back in. So I want to talk about some divisibility properties. And this is theorem 3.3, which is important because I'm going to refer back to these relatively often. So A1 divides A, and A divides 0. Here, maybe I should say A, B, C, X, Y, Z are all going to be integers. So 1 divides any integer, and any integer divides 0. If A divides B, and also B divides A, then, well, we proved that you can't be a divisor and be bigger. So A can't be bigger than B, but B can't be bigger than A. Our only option is A is either equal to B or the negative of B. Another interesting one, A divides B and B divides C. Then A divides C. That's going to come up a lot. Relatedly, if A divides B, then for all, this is theorem 3.3. What I'm writing out right now is theorem 3.3. Each of these is a part of theorem 3.3. For all x an integer, A divides B times x. So if I already divide something, if I multiply that something by an integer, then I divide that new thing as well. If x is equal to y plus z, and A divides any two of these numbers, then it must also divide the third one. And part F, if A divides B and also A divides C, then I can pick any x and y that are integers, and A will divide B times x plus C times y. So it's kind of a combination of these two statements that's going to be powerful. Okay. So these are our main tools. We've proven A. I'm not going to go through and prove all of these. Maybe I'll have you prove another one of these as a warm-up on Thursday. You're going to want to know these. Yeah, this is an important theorem. This is going to come up a lot. This is like your laws of logic or your laws of inference. When proving things about divisibility, these are going to be our main tools. So I want to do an example of how we can use these tools. To prove things, because we can make some pretty tricky questions now. So example, suppose that A and B are integers such that 17 divides 2A plus 3b. Prove that 17 also divides 9a plus 5b. Okay, so this is our goal. And I'll admit to you, the first time I looked at this problem, I thought it was going to be easy, and then it was hard. It didn't jump out at me right away. So one thing you might try is using 3.3 part D. And say, oh, okay, well, if it divides this, then I can multiply it by any integer. So if I wanted to say that 17 also divides 6a plus 9b, that would be easy. Because I could just say, oh, multiply the whole thing by 3. But there's no integer I can multiply 2a by to end up with 9a. So that doesn't work. And then this kind of looks like 3.3f, but it's in the wrong direction. Right, I have the conclusion. I don't have the premise. So that one doesn't help out. So the only thing you can do with these types of problems is play around a bit. So I know that 17 divides 2a plus 3b, because that's a premise. And now, what can I do? Well, I know that means 17 also divides multiples of 2a plus 3b because of theorem 3.3 part D. And the one that ends up being important is 17 divides 4 times 2a plus 3b, which is equal to 8a plus 12b. And this is by theorem 3.3 part D. Okay. I'm going for 9a plus 5b. What I have is 8a plus 12b. That's not super interesting. But I also know that 17 divides 17a plus 17b. Here I'm using theorem 3.3f. I know 17 divides 17 and 17 divides 17. Therefore, 17 divides 17a plus 17b. So this is a tricky idea. And then, I'm going to use another tricky idea. I'm going to use theorem 3.3f again to say 17 divides 17a plus 17b times 1 plus 8a plus 12b times negative 1. I'm using 3.3f again. I know it divides this thing by line 3, and I know it divides this thing by line 2, so I can use theorem 3.3 with those two numbers. And, like magic, because I worked everything out all ahead of time, this equation 17 minus 8 is equal to 9, and 17 minus 12 is equal to 5. So I have proven that 17 divides 9a plus 5b. But it's tricky. Doesn't come out immediately, right? This is, like I had said earlier, this is one of those proofs where when you look at it, you go, man, the guy who wrote that proof is sure smart and handsome, maybe just clever. But what you don't see is all the work that goes into it. What you don't see is the pages of scribbles where I tried not only multiplying by 4, but 2 and 3 and 5 just to see what I could get. And I got this 17, and I tried some other things, and things weren't working, and finally I figured out how to make this work. I figured out 4 was the right thing to multiply by. Right, so why did I choose 4 in step 2? Where does this 4 come from? Great question. Fantastic question. Answer, it's what works. How do I know it's what works? I didn't. I tried a whole bunch of stuff. I knew this idea was going to be useful somewhere from experience. And then I knew I had to use this 2a plus 3b somehow. So I just played around with some stuff. I tried multiplying by different values. I tried 2, I tried 3. One thing I tried at one point was 9. Here's a thing I tried that didn't work. I tried 9, so 17 divides 9 times 2a plus 3b is 18a plus 27b. And then I tried subtracting off 17. I got 1a plus 10b. Good question. So what I'm saying here is that this stuff in brackets is equal to 9a plus 5b. So step 4 is really saying 17 divides 9a plus 5b. But the stuff in brackets is the math I was simplifying. So right, this is a good proof. It's just not what I was asked to prove. I ended up proving 17 divides a plus 10b, even though that wasn't my original goal. So yeah, shock, surprise. We need to go back in case 4 won't work. In the exam, you have limited time. Is it just rolling the dice, right? It's not luck. There's some luck involved, of course, to think of 4. But there's 2 pieces of information you need. The first is, the more of these you do, the better you get at it. Right? I came up with this proof relatively quickly. It took me maybe 5 minutes. It wasn't the first thing I tried. This was the first thing I tried. But it didn't take me long to come up with the answer. The second thing you need to know is when we write test questions, we don't pick things randomly. We write test questions with answers in mind. So this number was 4. 4 was the thing that worked. The thing that works here is never going to be 700,432,812, right? We know you're not going to come up with that number. We wouldn't come up with that number. But these are things that you actually need to be able to prove. You need to understand how you can try enough things to come up with 4. And you need to be fast enough at trying enough things to come up with 4 that you can get there in a couple of minutes. So we do write test questions with your abilities in mind. We're not trying to fail everybody. That's not our goal. But this is a class about writing proofs. There is no process that you can follow that gives you the answer every time. It's not like calculus. In calculus, if you know how to do every problem, you just follow the same steps and you'll always get the right answer. And this is not that class. This is real math, not calculation. It's different. For some people, it's exciting. Some people hate calculation. Some people are like, it's so boring, I make a silly mistake every time, I can't stand it. This isn't that, I like that. Other people love calculation. It's comfortable, it's safe. I've learned the steps, so I know how to do it. I'm all good. This is the art of mathematics, right? Coming up with 4 is an artistic step. It's inspiration. I've seen things before and I'm combining them in new ways. And that's how we do new math. You need new ideas, right? All of this that we're teaching you, at least you know somebody's done it before. Think about that. Math research. You're doing math no one has ever done before. You have to come up with an idea that no one in the history of mathematics has ever thought of before. That's my job. We don't make you do that part. How did I do step 3? So step 3, I'm using part F. So I'm saying 17 divides 17, and 17 divides 17. So therefore 17 divides A and B, 17A plus 17B. This is 17 divides 17. Okay. This is a tough problem. This is something that you should definitely get some practice solving. Okay. Let's keep going. Let's prove some more things. Proving things is good. Let's prove some things about prime numbers. Theorem. I start getting lazy and just write THM instead of theorem. Every integer n bigger than 1 has a prime number p such that p divides n. And proof. How are we going to prove a statement like this? Every integer n bigger than 1, some prime number divides it. Any ideas? Give you a hint. It's a theorem about integers. How do we typically prove for all statements about integers? Yeah, really good. We're going to use induction. Let P of n be the statement there is a prime P such that P divides n. Really nice. Okay, what's our base case? We want this to be true for all integers n bigger than 1. So our base case is going to be P of 2. And P of 2 is true because 2 divides 2. And 2 is prime. So that works out well. Next we have induction hypothesis. I'm going to leave that blank for a second. Let's go on to our induction step. This is going to help us figure out what our induction hypothesis needs to be. So if k plus 1 is prime, if k plus 1 is prime, I don't even need induction. It just looks like my base case p of 2. P of k plus 1 because k plus 1 divides k plus 1. So if k plus 1 is prime, that's the easy case. We're all good. If k plus 1 is composite, if it's not prime, what does it mean to be prime? We said prime was you had exactly 2 positive divisors. So if you're not prime, you don't have exactly 2 positive divisors. But we know 1 divides k plus 1, and we know k plus 1 divides k plus 1, so there must be a third positive divisor b satisfying 1 is strictly smaller than b is strictly smaller than k plus 1. Has to be some divisor in the middle. If there were only 2, if this b didn't exist, then k plus 1 would be prime. Okay. This b is what I want to use induction on. Because if this b has a prime factor, then I can go back and use theorem 3.3 part C. So here's what I want to say. I want P of B so that P divides B and B divides K plus 1. So P divides K plus 1 by theorem 3.3 C. Right, that's what I want to be using. So in order to make that happen, my induction hypothesis, I need to be using strong induction. Right? B is not necessarily K. In fact, I know it's not K, if you think about it carefully. So for my induction hypothesis, I'm going to say let K be greater than or equal to 2 and assume P of 2 and P of 3 and all the way up to P of K. So now I get P of B by induction hypothesis. So P of 2 and all the way up to P of K, where somewhere in the middle here I have P of B, implies P of K plus 1. So in both cases I get, since K plus 1 is true if it's prime, then since P of K plus 1 is true if K plus 1 is prime, and P of all of this implies P of K plus 1, even if it's not prime, I get P of 2 and all the way up to P of K implies P of K plus 1, and P of n holds for all n greater than 1 by strong mathematical induction. So any integer you know has some prime that divides it. And we can actually do a similar proof. Oops, ran out of paper. By a similar proof, we can actually prove a little bit stronger. So theorem every integer greater than or equal to 2 has a prime decomposition. So a prime decomposition is that there exists P1, P2, all the way up to Pk. Each P sub I is a prime. And n is equal to capital pi for product. The product of all of these primes. Another way of saying this is factoring works. So if we have something like 36, 36 is equal to 2 times 2 times 3 times 3. Right? That is a product of primes. You can always keep breaking down your number until it's all primes. So I'm not going to write down a proof for this in the interest of time, but this proof is very similar to the proof we just did. You're going to take a number by strong induction. You can either it's prime already, in which case it is already a multiple of primes, or you can break it down into two smaller things. Each of those has a prime decomposition. You stick those two prime decompositions together, you get a prime decomposition for your bigger number. How do you read the notation? This is n equals the product from I equals 1 to k p sub I. So sigma notation is the sum, pi notation is the product. Yeah, if the number is prime, then k is just 1. I just have one prime number. The prime factorization of 37 is 37. This is a list of prime numbers being multiplied together. The list just only has one number on it. A good question. This is important. It's not times 1. It's not times 1 because 1 is not a prime number. Right? We defined a prime number to be bigger than 1 in the definition, and also to have two different multiples. So this is pi. Pi does mean multiplied. It's a little bit hard to show in writing, but in handwriting, this is a capital Greek letter pi. So capital pi versus a lowercase pi. So the Greeks also have capital and lowercase letters. This is the capital, which we use for product, versus the lowercase. This is also a capital sigma versus a lowercase sigma. Just that capital pi and lowercase pi look similar and can be confused, whereas capital sigma and lowercase sigma do not. But S sigma sum p product pi kind of goes together. Yeah, exactly. So sum from I equals a to b of f of I is f of a plus f of b, f of a plus f of a plus 1 plus f of a plus 2 plus all the way up to f of b. And product I equals a to b f of a sub I, f of I is f of a times f of a plus 1 times f of a plus 2 times all the way up to f of b. Yep, so if you add, you use sigma. If you multiply, you use pi. All good questions. Okay, let's do another theorem. There's a nice comment about this, but I'm going to skip over it in the sake of time. Theorem, again, a thing that seems true, but we should prove it. There are infinitely many prime numbers. So this is one of those things where it's like, yeah, okay, I think that's true, but how do you prove it? Not immediately obvious. Right? It's not really something you can prove by induction because not every number is prime. And it's not like if you take a finite number of primes, that gives you a finite number of numbers because, 2, 4, 8, 16, 32, 64, 128, 256, those are all just using 2s. I haven't even introduced any other primes. So the proof of this is going to be our first example of a proof by contradiction. We saw a little bit of this in our logic section, but now we're actually going to use it to prove something real. So how does proof by contradiction works? We're going to assume the negation of our statement, of our claim, and find a contradiction. Conclude something false. So the logical thing we're using is that from not P implies falsehood, we can conclude P must be true. If the negation of your statement leads to a contradiction, then your original statement must have been wrong. You can conclude, or your original statement must have been right. The negation of your original statement must have been wrong. So what is the negation of our statement? We're going to assume, for sake of contradiction, and since so many proofs start out like this, assume for sake of contradiction, that this is sometimes abbreviated AFSOC, assume for sake of contradiction, that there are not infinitely many primes. Well, if there's not infinitely many, we can list them all out. Then the primes are p sub 1, p sub 2, all the way up to p sub k. That's all of them. And now I'm going to look at a particular number. N is going to be 1 plus the product of all of those primes. Okay, I'm picking this particular integer. Here's the trick. N is bigger than all of these numbers, right? It's bigger than 1 plus p1, it's bigger than 1 plus p2, all of them, or greater than or equal to, so it's not on this list. N is not on the list, so it is not prime. Since it's not prime, that means one of the primes must divide it. Let's call that one p sub I. So p sub I divides n, and also p sub I divides the product from I equals 1 to k of p sub k, sorry, it's a typo, that should be p sub I. This is just because this is p sub I multiplied by a bunch of other stuff. Therefore, by theorem 3.3f, p sub I divides n times 1 plus this product I equals 1 to k of p sub I times minus 1. But this number, remember, I defined n to be 1 more than that, so when I subtract that off, I get p sub I divides 1. And this is not possible for a prime number. But p sub I is bigger than 1, because it's prime. And we proved, we had that theorem, a bigger number can't divide a smaller number. So I'll just say, so -1 is less than or equal to p sub I is less than or equal to 1, and that's our contradiction. So we assumed that there were not infinitely many primes. That led to a contradiction. So we conclude there are infinitely many primes. Okay, sorry for running a couple minutes over there. I'll stop there. Into divisibility. Stop the recording now, but I'll hang out in case there are any questions.